Hello guys, welcome back to Tronics Energy. We are still in our series of understanding registers, how they operate, and the different types of registers that are out there. We started off with the serial input, serial output, and some couple of videos back we did a 2-bit. We started off with a 2-bit serial input, serial output that we connected using logic gates, making the D flip-flops and connecting their clock inverted so that we can achieve a serial input, serial output. Then in our last episode, we started off, or we made a 4-bit serial input, serial output using an IC 74LS195, which as we said, it's quite you can call it a general purpose register, because it has connection of parallel, serial, and all other operations that you may need to make a register. So last time we did a 4-bit serial input, serial output, and I explained how you can make it using our IC right here. So we use pin number 2, pin number 3 as the input of the serial. Then pin number 10 was the clock, which is fed into all these D flip-flops which are inside the IC. Then pin number 9, we kept it high. We connected it to the power supply so that it can disable the parallel section of our circuit, because we are not using the parallel input. We are using the serial input section of our IC. Then pin number 1, we also kept it high because because we say that pin number 1 is clear. The pin is clear. So for us to be able to operate our IC, we need to keep it high so that it does not clear what we are doing as we want to process data, or as we want to see the output, or when we want to feed data. Because once it's off, if it's off, nothing is really going to happen. Even if you feed data in your IC, nothing is going to happen, because this you will have enabled this clear section, which is not right. Yes, so this we keep it high. Even in our connection today we are going to keep it high because we want to use our IC. So set pin number 1, we just keep it high. And today we are going to do a parallel input, parallel output, parallel input, parallel output, meaning that we are going to use all these parallel connections. This will be our inputs, and this will be our outputs. So the difference between a parallel input and a parallel output compared to the serial in, serial output, is that this you enter data into all those 4 flip-flops each at a time, and what you put into the input goes immediately to the output, and nothing changes until you turn the input off. So you can see here, this P naught, Q naught. So P naught and Q naught are connected together. So once I put this P naught is the input, is the parallel input. This is the parallel input section. 4, 5, 6, 7 pins are all the parallel inputs. So if I put P naught on, then Q naught will be on automatically. If I put P1 on, Q1 will be on, and it's immediately. Once I turn this on. Once the clock is aligned with the input, the output corresponds with what you have put at the input. So each flip-flop is controlled by its own data input. They are not connected. This once you enable this parallel enable, then the circuit operates in a way that all flip-flops are operated with their data inputs. So these are the different data inputs of and these are the different data outputs of the flip-flops. So I hope you've understood that. Last time I had drawn a parallel input, parallel output, so I'm going to use that sheet, that paper, instead of that one. So this is an example of a parallel input, parallel output, how it looks inside. So right here we have the 4-bit data input, because we said that our IC is a 4-bit parallel input, parallel output. Is a 4-bit 4-bit IC. So we have the data input here, A, B, C, and D, then the output right there. So you can see each flip-flop is controlled by its own data input, and it gives its own data output. And the clock signal for this connection is connected directly to all flip-flops are connected directly. They are not inverted, and they only process data when the clock signal is high, or the rising edge of the clock signal is only when the flip-flops are going to be activated to the what you have put at the input. So I hope you have understood that. So we're just going to connect a parallel input, parallel output, and to connect that using our IC right here, we are going to connect inputs from pin number 4, 5, 6, 7. Then the outputs are still going to be the same as we had made last time. And another thing you should know about a parallel input, parallel output is that the data does not shift. The data does not shift, meaning that what you put at the input will remain at the output until you change the input again. So it's not going to shift from flip-flop to flip-flop. It's going to remain the same, even though the clock is going to be on and off. So the data here does not shift. It remains in the single state that it was until you change what it's in the input. So that's the other difference of a parallel input, parallel output. So the connection is just simple. We have said that this pin number 9, now we are going to connect it to ground rather than connecting it to power supply, because we want to enable pin number 9. Once we have enabled the parallel section, this J and K is meaningless. You cannot use a serial in because we have enabled the parallel input. So meaning that our circuit will be parallel input, parallel output only. This J and K is you cannot operate anything there. Same. And as we said, this logic, this is the logic symbol of our IC. You can see some pins are not here. Pin number, I think pin number 8 and pin number 16. So pin number 8 we say that it is ground, and pin number 16 is a power supply VCC. So you should check the data sheet of this IC. You check the maximum ratings of the power supply before you start doing your operations. So this is the IC, this is the connection. It's just the same as last time, only that this time round we have the 4 inputs. These are the 4 inputs, these are the 4 outputs. Okay, so this deep switch is going to control all those 4 different operations. It's going to control all those 4 different operations. Yeah, let me just turn them off so that we can start all together. Yeah, I think they're fine. Here we have the clock signal, and I'm using a 220 microfarad capacitor in the oscillator mode of the NE555. It's a bit slower, but as we said, this is not the real speed of a processing unit, because we want our devices to be fast. The speed of, or the measure of the clock in a system is measured in nanoseconds, so meaning that they are really fast. So I'm using these capacitors. They are quite slow, just for us to understand how things operate inside our system. So I'm going to turn on my power supply, and yes, it's on. You can see the clock has already started blinking on and off. So this is the clock signal, and as we have said in our sheet here, the clock is connected directly into all those flip-flops. There's no inversion as the compared to the serial input, serial output, because the serial input, serial output, the data can be processed either in the rising or the falling edge of the clock signal. But in a parallel input, parallel output, it's connected. The clock is connected to all flip-flops together, so they only process data in the rising edge of the clock signal, all these flip-flops. So we have said it does not shift. So once I put on right here for number 1, it's going to turn this LED on. This is the output of this flip-flop, and nothing is going to happen until I turn that off. So if I put it on, I wait for the clock signal. If I put it on, it's not going to change even if the clock is on and off. It's going to remain like that until I turn it off when I want. I turn it off like that. So let's say we have a data like or let's just use this one, 1010. So 1010, we are going to feed it in all 1, this 0, then number 3 is on, like that, 1010. So we have stored 1010, and nothing is going to change until I change the input, until I change the input into what I want to store next time. So this does not change, it just remains like that. Compared to the shifting compared to the shifting of the serial input serial output, the data could have already started moving from the first LED to the last LED. So yeah, like that. So we can store another data like, let's say 1101. Use this one. So 1 1 1 0, then 1 1, like that one. So 1101. So 1101 is in our circuit, and like that. So it has stored that data, and nothing is going to happen until I turn those inputs off. So in a system that uses a parallel input parallel output, the data fed to the registers, or the data fed to the registers, does not come into bits like the way I'm turning this on. It comes all at once. If it's 1101, it comes all at once into the inputs of those flip-flops 1101. Then it automatically changes the output into what you have in the input 1101, like that one. Yes, compared to the serial could have started with the least significant bit 1, then it goes to 0, then it goes to 1, then it finish up with the most significant bit, which is 1 there. So that's basically how a parallel input parallel output shift register operates. And yeah, that's what I wanted you to see today. You can see this is quite simple, quite a simple circuit. Yeah, so next time I think we are going to do serial input parallel output. I don't know if it can do that. Maybe I check this IC well to see if it can do such an operation, a serial input a parallel output, serial in parallel output. You are going to check if it can do this. If it can't, then we are going to check if it can do a parallel input serial output, whichever. So if it can't do all this, then I'm just going to look for another IC to do this operation. There's an IC called 74, I think 74HC or 74LS595, which is a 8-bit register. I think that one is quite good for mostly all operations you can do with it. Yes, so that's what I wanted you to see today, and thank you very much guys for watching. Please subscribe to Tronic Synergy, where we do fun stuff all day all the time. Hope to see you next time. Goodbye.